Alright, let's start by talking about what TQN is and why it was needed in the first place. So Q-learning on its own works fine for simple problems where you can actually list out all of the possible state action combinations. But once the state space becomes large, that approach breaks down. You just can't store all the values anymore, and even if you could, learning them would be way too slow. And that's where DQN comes in. The idea is to replace the Q table with a neural network. Instead of storing individual values for each state action pair, the network takes in the current state and outputs Q values for all possible actions. This way, the model generalizes across similar states, which is something the table-based approach can't do. And DQN was first introduced by DeepMind around 2013. It is actually a method that made headlines because it learned to play a bunch of other games just from raw pixels, just the same algorithm applied across different environments. So the network sees images, processes it, and tries to estimate how good each possible move is. And now let's break down how this neural network is structured. At the start we have got the input layer, you can see. This is where we feed in the state. If it is a game, that could be an image or maybe a few consecutive frames stacked together. If it is another kind of environment, it might be numerical features instead. The point is, this layer just receives the current state in whatever format we have chosen. Next, we pass that through the hidden layers. These are typically convolutional layers if you are working with images, because those are good at extracting visual patterns. But if the input is more structured, like sensor data or table information, then fully connected layers might be more appropriate. Either way, these layers are responsible for figuring out the relationships between the features and learning the patterns that matter for decision making. Finally, we have the output layer. That's where the network gives us one Q value per action. So if the agent can choose between, say, four different actions, this layer will output four numbers, one for each action, and the agent picks the one with the highest value most of the time, unless it's exploring. Now, there are a few extra parts that make the DQN actually trainable and stable. Just having the network is not enough. And first, there is the Q network itself. That's the main neural net that's learning to approximate the Q function. It is the one that we use to choose actions during training and prediction. Then we have got the target network. This is just a copy of the Q network, but instead of updating its weights all of the time, we only update it occasionally. So we can use it to calculate the target values during training, and this keeps the learning process more stable because the targets are not constantly shifting. Replay buffer. What this does is store past experiences, things like which state the agent was in, what action it took, what reward it got, and what the next state was. Instead of learning from each step right away, we save a bunch of these transitions and then sample a batch of them later. This helps break the correlation between consecutive steps and avoids outfitting to recent experience. And mini batch training here. So rather than updating the network after every single action, we sample a batch of experiences from the buffer and use that to perform a gradient descent step. This kind of batch training is more efficient and works better in practice. And algorithm time. As always, we initialize everything first, both the Q network and the target network and the replay buffer. The weights of the Q network are set randomly at the beginning, and the target network is just a copy of that at this point. The replay buffer is empty, but we define how much data it can hold. Then for each episode, which is just one full run from the beginning of the task to some endpoint, we start in an initial state. That state gets pre-processed, especially if it is an image, to make sure it is in the format the network expects. And during each step in the episode, the agent has to decide what to do. Sometimes it takes a random action, but most of the time it picks the action that gives the highest Q value according to the current network. Once the action is taken, we get back a reward and the next state. The next state is also pre-processed. Then we save the transition into the replay buffer. And at this point, we can sample a mini-batch of these saved transitions and use them to train the network. For each sample in the batch, we calculate a target Q value. If the episode ends right after that sample, the target is just the reward. If not, then we add the discounted Q value of the next state, but this part is computed using the target network. Then we update the main Q network by minimizing the difference between a predicted value and this target value. We do this using gradient descent. Every few steps, we also update the target network to match the Q network again, and that keeps things stable. Okay, and key innovations. And now we will look at what really helped DQN succeed. These two features, experience play and the target network, might look like small tweaks, but they actually fix some serious problems that come up when training neural networks with reinforcement learning. And first, experience replay. One of the issues in reinforcement learning is that the data comes in sequence. So if you learn from it directly, you end up training the network on highly correlated data points. And neural networks don't really handle that well. They start overfitting to recent transitions, and sometimes they even forget things they learned earlier. So instead of using the most recent data point, what DQM does is store the experience into a replay buffer. Then during training, it pulls random samples from this buffer. This breaks the correlation between consecutive steps. It also means older experiences can be used again, not just once and forgotten. So the agent doesn't just learn from what happened now. It learns from a much broader set of situations. And target network, let's talk about it. This was another key fix, and the problem it solves is something called the moving target issue. When the Q values used for training are based on the same network that's also learning, the targets keep shifting. So you try to optimize something that's changing while you are trying to optimize it. And that leads to instability, and in some cases the values just explode or collapse completely. To handle that, DQN introduces a second network, the target network. This one is just a frozen copy of the main Q network. It doesn't get updated at every step. Instead, we update it only once every few steps. Let's say every 1000 or 10,000 iterations. And that way, the target values used during training remain consistent for a while, which makes it much easier for the Q network to actually learn something meaningful. And we have a table here, and let's quickly compare. So classic Q-learning uses a table. Each state action pair has its own cell in that table. That works fine when the state space is small and discrete, but the method is evolved in anything more complex. In contrast, DQN replaces that table with a neural network, and instead of hard coding values for every possible station, the network learns to generalize across states. So if two stations are similar, it can give similar outputs, even if it hasn't seen both of them before. And I'm looking, the update mechanism is different too. In traditional Q-learning, you just adjust one cell in the table. But with DQN, you train the whole network by minimizing the difference between predicted and target values using gradient descent. Also, Q-learning only learns from the most recent experience, one step at a time. DQN instead samples a whole batch of experiences from the buffer. And this makes learning more stable and also more efficient since each piece of experience can be reused. That's okay, and the way target values are computed is another difference. Q-learning uses current Q values, which again means the targets can shift during learning. DQN fixes that by using a frozen target network for a while, so those values don't move around during training. And memory usage is also handled differently. Q-learning grows with a number of state action pairs, so the bigger your space, the more memory it eats up. DQN only needs to store the weights of the network and the replay buffer, both of which have fixed size. And generalization, let's look. With Q-learning, you can't generalize. Each state needs its own slot. If the agent ends up in a state it hasn't seen before, it knows nothing. But DQN can generalize across similar states because that's what neural networks are good at. And variants here. What are they? First, double DQN. Here, one of the issues with standard DQN is that it tends to overestimate Q values. It picks the action with the highest predicted value, but because of noise or randomness, this value might be higher than it should be. Double DQN splits up the rows, the online network selects the best action, and the target network evaluates it. That makes the value estimates more reliable. And prioritize experience replay. Normally, experiences are sampled randomly from the buffer, but not all experiences are equally useful. Some prioritizations, especially those with high error, are more informative, and prioritizer play picks those kinds of samples more often, which means the network focuses more on learning from the situations that it's struggling with. Dual-link DQN is another trick, and here the network architecture is changed so that it separately learns two things: how good the current state is on its own and how good each action is in that state. And this makes it easier for the agent to understand what's going on, even if the difference between actions in some states is small. And Rainbow DQN, this one just combines all the improvements I have mentioned into a single algorithm, and it is not doing anything brand new, just putting together all the parts that work well. And distributional DQN takes a different approach. Instead of just predicting the expected reward, it predicts the whole distribution, meaning it captures uncertainty about what could happen. That's useful in settings where outcomes vary a lot and you want the agent to know not just what's likely, but also what is possible. And finally, there is the noisy DQN. Normally, exploration is handled using things like epsilon grid strategies, and noisy DQN adds noise directly into the network weights, so the agent explores automatically without needing a separate randomness mechanism. It makes the behavior more consistent and the code cleaner. And that's okay, and that's all for this lesson. Thank you for listening.